And today, I will talk about why and when a CPU is sufficient for your business AI needs. Before we jump into the presentation, I would like to spend some time talk about myself and why I come up this topic. So I have roughly 10 years of data science working experience. And before joining Lenovo, I'm working in mostly in the research and the development team. So most of my work is to train the model, evaluate the model, and monitor the model. So I don't touch deployment phase. I work with engineering team to deploy all the models so that clients can use it. But most of the feedback I receive from them is we need a model that is smaller, simpler, and faster. So after I don't quite get why this is so difficult to deploy the model. Even though now I joined Lenovo, so some of my responsibility shift from AI data scientist or trained model to AI deployment, like an AI engineer. And I start to feel the pain why hardware issues, memory issues are so critical when deploying model. As we all know, in AI, NVIDIA GPU dominates the market, and every company, every enterprise are fighting for it. And the number of the NVIDIA GPU becomes one of the critical metric to measure how powerful your AI team is. The same thing happened to Lenovo. We fight for the GPU while waiting. We just do different benchmarking, we do different testings. So with all the overwhelming number of models, number of GPUs, I suddenly realized there is a sweet spot where CPU aren't just good enough, but actually there's a smarter and a cost-effective choice for many business use case. So today, I do a demo to show why I came up, how this topic stands. So let's get to it. So in this presentation, I will cover how large language model consume computing power, either memory, energy, etc. And what are the popular large language model architectures, and what are the limitations, what smaller language model can do, and lastly but not least, what you should consider when deploy a local language model to your business. So nowadays, we know there are lots of frontier LLMs, around 40 popular LLMs on the market. And when you log into Hugging Face, there is over 1 million models. So for beginners or who are just starting AI model, it easily gets overwhelmed. So on the left side, on the right side, we can see these are famous far and wild names like GPT, Gemini, Llama, Cloudy, and Mistral. Some of them we use on daily basis, either through API call or we download a model, which some are quite big. And we see like GPT-4, it has 8 times 220 billion parameters. So we can see all of these models have billions of parameters, and some even hundreds of billions parameters. So this raised me a question is, how do we run these locally? And even though some are open source, with Llama 3, we have 400 billion model that is available, but how to deployment on our hardware becomes a critical question. So first thing, in order to run this model, these are very famous, these are very useful. The first question is, what's the minimum memory requirement to run a large language model? How to load it? What's the hardware requirement to load just one single model? So we can see this is the formula where M is the memory expressed in gigabytes. P is the model size, which is the number of parameters, and Z is the quantization factor in bytes, and we know 1 byte equals 8 bit. And 1.2 is represents 20% overhead of loading additional proc. So this is like set aside memory just for some other product usage. So for different precision, we know the most popular one is floating point 32, and it will come with it was 32 bits, which is 4 bytes. So the factor is 4. And if it's FP16, it's 2, and et cetera. When it's in 4, it becomes 0.5. So now let's see some examples. Okay, so let's say for 8 billion model, which is at 32 floating point, plug into the formula, we will see it's equals 8 times 4 times 1.2. So the memory required is roughly 38.4 GB. And we go to, if it's 70B, even a lower precision, we have ended up 84 GB. And even bigger model, even it's integer 4, we will need 243 gigabytes just to load the model. We are not just to load the model in order to run. So if we have a GPU memory lower than this, we will go to memory out of memory runtime error. So which is always frustrating in the engineering. And and this is just load memory. So in order for you to interact with these models, of course, there will be multiple turns. It will create another thing called KV cache. So I remember there is another professor demonstrate how KV cache works and why it's important. Because for most of the decode model, the new output will become the input in the next generation. So because of this autoregressive fashion, if the output generated 100th word, the time to generate this word will even more than the previous 99 combined. That's why we introduced the KV caching to save time and computation cost. But as we all know, there is no free lunch. Everything comes at a price. In order to increase the latency, decrease the latency, increase the cost efficiency, we trade space as time. So that's why we create a KV cache. So for KV cache, I will provide example how we calculate it. So this is a formula. At first, it's more complicated than the memory, but let's go through each one by one. So first M is the memory. Is the memory take to the KV cache, and 2 is the factor. Since we will store 2 vectors, key and value, so we will multiply everything by 2. And C is the number of concurrent users, and T is the average context token, which is the token sequence length per user, and L is the number of layers in the transformer. So different model will have different layers, and N is the attention head, etc. D is the dimension of each head, and C is, of course, is the quantization again. So let's go through a real example. So let's consider an organization. They want to implement the Llama 3.3, which is a 70 billion model at precision 16 for 100 concurrent users. And we say the average context is 8,000. And so given that this model, Llama 3.3, it has 8 layers, 64 attention head, 8 KV cache head, and 128 head dimensions. So we will end up the memory of KV cache roughly 262 gigabytes. So with this nature, the size of the KV cache could easily pass the size of the model, even though the size of the model is super big. But during inferencing time, when we interact with LLMs, it's normally will have several turns back and forth. The conversation won't end with one turn. So it's easily the memory requirement gets tripled or even 10 times if we implement a much bigger large language model. So in this case, we will require around 430 gigabytes in memory, just in memory for one turn. So up to here, I feel, go back to my old question is, if the large language model are so popular and they are so powerful, why aren't they everywhere? So we can go, after doing some research, we can see, of course, it's due to the high cost and the resource consumption. So the substantial financial and energy requirement of large language model hinder their widespread adoption. And of course, second is the privacy concern. Dependency on a remote server introduce delays and raises data privacy issues. So my previous work is at a financial institute, at a fintech company. So our clients are all from financial institutions. They are very serious on the data security. With that, almost all models have to be local, have to be on-prem, and there's will be minimum API core. That's raised another issue. That's raised a question, raised the situation. I barely use the AI model, especially for closed-end, gigantic, large language models. And third is the challenge in personalization. So to fine-tuning these large language models to specific tasks or users is often impractical because they are very large. They are more of a fit-for-all purpose large language module. They might be very good at answering questions at PhD level, like how universe is formed and what's the history of human being, but they probably will struggle to answer a question like what's Oliver's shoe size, right? Oliver is my son, by the way. So how to make these large language models for your use becomes a hard question. And lastly is the efficiency in edge computing. So large models are very difficult deployment on edge device, so where computational resources are very limited. So now what I think is what we can do, even though there are so many powerful large language model, but we can use it for our specific use. Then just imagine there's a language AI that is capable enough to address your specific needs, but runs directly on your phone, on your tablet, or even your watch in near real time, and consume only a few watts of energy. And most importantly, does not need internet access. So what do we need here? A smarter, a leaner, a more efficient language model. Let's hold the answer for now. Let's take a step back and look at very famous large language model architecture. This is kind of like a household name of the AI model, transformer. So we know there are normally two towers. One is encoder and the other is the decoder. And let's see some models is encode only, some are decode only, some use both towers. And they will serve very different use cases. And I list out some specific use case here. So for encode only, we have BERT or Robota. And some use cases that can apply to is like sentiment analysis, text similarity. We can use encode only to create embedding on sentences, then calculate the similarity of two sentences. Or we can do named identity recognition. So for each sentence, we can recognize either it's a people's name, either it's a location, or it's what else? Name, location, etc. Some famous, well-known names, right? And there's a decode only large language models. We know the GPT series are very famous, and the Llama series and the Cloudy for sure. And these are for text generation to creative writing or conversational AI. So more of a generative, have a conversation with human beings, which interact with humans or clients. And also we have encoder decoder. architecture, which we have T5 or BART, and the use case with them could be translation. So it's more of a sequence to sequence large language model, and we can do summarization. We give them a long context and summarize what we need, and also Q&A. So next, I will roughly introduce some of the model names per each architecture. So for each architecture, I will provide one model is with smaller size, one with middle size, and one with larger size. So we can see for encoder, we have BERT series from 66 million to 340 million. And for decoder, we have Llama 3 from 1 billion up to 70 billion. Of course, we know there is a 400 billion or even more, and we have DeepSeek, we have Oven, like DeepSeek R1, we have which scaled up to 671 billion parameters, which is quite large. And next is encoder decoder model. We have T5 base up to T5 XXL, which is around 11 billion model. So some key takeaways is we can see the range of the model size shows a significant difference among various architecture. And the encode-only model tends to have smaller size compared to their peers. So what it means is the model sets can have up to 25,000 scale difference when during the deployment phase. So let's go back to what we need. So up to here, what I thought is if we could have a smaller, more focused, and customized language model that can meet your specific needs. We know that large language model, they are less governed, they are more generic, and we can use this model, or we can find a small model, fine-tune it into our specific needs to make it become a more government and excel at a specialty. Can we do that? Let's see the steps to implement a comparable small language model. So first, we need to define a task and select a base model. So first, like identify a specific use case. Either you want to write text generation, either it's sentiment analysis. Then you choose a model type based on the task. So for the based on the list I provided, for different use case, you should choose different large language model that best suits it. And lastly is to match model size to your hardware. We know hardware is the key. It can hold either it's 1 billion or a couple of 100 millions of model of yours, right? Then this give us a starting point. And after this, we can select adaptation strategy and the data. So for fine-tuning it, we can choose LoRa for efficiency or for fine-tuning the model for maximal customization. And of course, data is the key. We need to select qualified training data to match the use case. And the last then is evaluate and optimize. So we need to test the performance on the task specific metric. Either suppose for sentiment, it's either 0 for match, or 0 for not match, or 1 for match, right? Or for other Q&A, we have exact match, or we can choose the F1 score, like see how many words in the answer match to the ground truth. And after we evaluate, we can quantize or compile for efficient inference. So quantization is to choose a lower precision model, and for compile is to either use software or hardware technology to boost the AI inferencing. Okay, so speak much. When going to the AI engineering, we know talk is cheap. Show me the code. I will go through two examples with you. I will go over two examples with you. So let's see. Can you still see my screen? Okay, cool. Uh, so the first use case I select is about sentiment classification. So what I plan to do is I will run a Llama 3 8 billion model on as is on the GPU, and we will calculate the runtime, the accuracy, and the memory it used. And then I will run the BERT large model as is, check the same metric. Then I will fine tune the BERT model, see what we improved, either the accuracy or the runtime. So to save time, I have the output here already. So we see the inference time. We go. The data set I run on is called Stanford SST2. So Stanford and thematic data. So this is a sample data. We can see it's for the review. It provides a review, and the label is either it's a positive review or it's a negative review. Let's see one sample. See like that loves its character and communicates something rather beautiful about human nature. So we can see it's positive, and it contains no weight, only labeled gigas. And we know this is a negative review. So what this does is it will tell us, sec. So we test on the roughly 840 validation set and check their accuracy. So we see when we run this model on Llama 3 8 billion, the accuracy is around 90%, pretty decent, and it runs about 5 minutes. Okay, and if we run on the same model but with CPU, it goes the runtime of course goes above. With every other things are similar, so it goes about 16 minutes. I assume, yeah. So if we use BERT large as is with nothing fine-tuned, the time decreased dramatically. We see it only takes about 27 seconds to have the result, but the accuracy is quite poor. It's only roughly above 0.5, so it's like a barely guess, right? So next is I want to fine-tune the model. I use the LoRa method to fine-tune the model, and we can see the inference time only increased a little, so from 27 to 28, but the accuracy jumps to 29%, which is pretty good. So what it tells us. So here is a summarization. So here it summarizes for Llama 8 billion, it runs about 5 minutes. It takes the system RAM about 1.4 GB, and the GPU VRAM, it takes about around 16. And for BERT LoRa, it runs 28 seconds and consumes nothing on the GPU, but it takes 3 GB on the system RAM. And here is an Apex, which is Intel extension for PyTorch. This is one of the compiler or accelerator I used at software level. So Apex is Intel technology that it will boosting the memory, increase the memory efficiency and boost the matrix multiplication during neural network. And while I implement this, the accuracy is the same, but the runtime is decreased by around 30% from 28 seconds to 20 seconds. And the memory it consumed also decreased from 3.3 gigabytes to 2.5, keeping everything else the same. So what we can see is the runtime on large, keeping the same accuracy. The big large model runs 15x more than the BERT LoRa method, and the power consumption is 1.6x more. And here we only consider the GPU and the CPU power. And if we can take into like a cooling system into consideration, it can easily go above 2x of even the consumption can easily go like doubled or tripled. So this is one, and the other use case I want to show you is on the Q&A, and the data set is same. What I use is I will use a T5 X large, which is 2.35 billion model, and run as is on GPU, and I will use T5 base model, then fine-tune the base model. And the data set I'll use is a squad. Let's take a peek of what squad looks like. So this is more of a provide a context and provide a question and what kind of answer it will generate. So here is so the metric I'm evaluating here is either exact match. It means the answer exactly to the exact same to the ground truth, or the F1 score. The F1 score is a combination of recall and precision. So we want to know how many correct answers appeared in your predicted answer. So we can see for the X large, we have X match 0.8 and F1 score is 0.87. And the runtime I saved somewhere. Okay, we can circle back on this. And for this is the blend base as is. So for as is, we can see the exact match is lower, but still decent. But consider I only took 200 samples, so the exact match is 0.7, and F1 score is 0.8. And after I fine tuning it, it's been boosting to what the X large model can do. So here is a summarization. So the runtime, the model size increased a little because of the LoRa added more two more matrix adapted to the original base model. So we can see the exact match is same, but the runtime is much less. And here I didn't put into the CPU and GPU consumption, and we all know that T5 base is running on CPU, while the T4 XL is running on the GPU. So let's see a UI. So with Q&A model, I would assume it will be capable of to answer questions that is specific. Okay, I create this UI with the help of Cloudy, of course, and I implemented 3 models, which is LoRa T5, T5 base, and T5 X large. And the questions I will be asked is, let's see, Kelvin He's resume below. These are my resume. And let's see, when did he got his first job? Now we implement is, let's go from here, X large. Okay, so let's see. It got an answer right. It's April 2014. That is when my start. And now let's see if it's a base. So see, if it's a base model, it got wrong because it only extract the latest date in my resume. So if we have the LoRa, okay, let's see if it can get it right. Oh, no. Okay, so the LoRa didn't get it right. It's kind of embarrassing, but let me see. Let me try another. Let's see, where did Kelvin He start his first job? Okay, it says JP House Corporation, which is right. And let's see what base can do. So here, see, this shows some difference. Is for the base, it only extracts the latest company, and where after it's fine-tuned, it can get a more precise output here. So yeah, once we know, I only choose a very small data set to fine-tune it, just to showcase what a good quality data fine-tuning could help a small language model excel and how they can generate a more accurate response with accuracy similar to a large scale, 10 times than itself. So we can, let's check this one. Oh, it says Tokyo. So you see, for the same question, large language model and the LoRa shows different, but still decent answers. Okay, let's go back. Now we know after fine-tuning a smaller language model, what it can do. What's next? So when we deployment, whether we choose on-premises or cloud. So there are different comparisons. A lot of aspects need to take into consideration. So here I list some. Of course, the top one is the cost. So with on-premises, the upfront cost will be high because you have to purchase a lot of hardware, storage, networking, versus cloud, you don't need to hardware investment. You pay as you go. And they, even like AWS or Azure, they provide 1 year or 3 year saving plans. So it will even lower the cost. And of course, for ongoing cost, for on-prem, you will need some maintenance fee, but it will relatively low compared to cloud because it's keep running. From if you have the instance running 24/7, it will cost you 24/7, right? And for other aspects such as scalability, performance, latency, or security, etc., etc., etc. And here I took an example to do the comparison. So I took one of the ThinkSystem device from Lenovo and versus cloud. So this ThinkSystem device equipped with two Xeon CPU. So it was across with 512 gigabytes in RAM. It's approximately $12,000. And let's assume the ongoing operation expense was about 500 per month. And then for the cloud, I try to select a very uncomparable instance, which is R7i 8X large, which has a 32 vCPU and 256 gigabytes RAM. With two of them, the monthly cost will be around 1,400 for a 3-year savings plan. And on the right side, you can see this is the graph. The red one is the on-prem. It has a higher upfront cost, but when you implement the model as time goes by, it's more flattened than cloud implementation. So we can see the break-even point is around 13 months. So what it tells us is if you want to mm, implement your AI solution more than 1 year or 13 months, or at some threshold, this is the way you can compare two strategy, which way to choose. And last but not least is to advertise our Lenovo AI infrastructure and devices. We not only sell laptop and a ThinkStation. Our team would focus on the Think Edge. Like I mentioned, we will deploy small language models on this edge where computation resources are limited. And we have the Think system for high performance computing or some large language model computing. And lastly, these are all the appendix. So these 3 papers I published is written by me and published on Lenovo Press. And we have the LLM sizing guide and the fine-tuning LLM using Intel Xeon CPUs and some product guidance for V3 and V4. And welcome to review all of them, get know more about large language model, and I hope this story holds. When the large language model is not nearby, there are good candidates that we can select. We can fine tune it, and consider a small language model is an assistant of ours who needs very detailed micromanagement so that they can serve us in specific needs.